So this is an interesting application of an exponential growth decay type problem. And what we're doing here is we're setting up a situation where you have two different rates going on. In one of these cases, you have the California growth rate, and in another, you have the Texas growth rate. And I picked 2 years here, the 2016 population of each state and the 2022 population of each state. And you can see here, there's something going on because Texas has a population that is going up and California has a population that is going down. And I mean, there's a variety of reasons for that. For one thing or another, California kind of sucks. Who knows if this will actually continue in the future, but let's just, for the sake of this problem, assume that these growth rates are going to be constant, okay? Now, first thing to do is actually calculate what those growth rates are. So let's go ahead and do that. Let's look at California's growth rate over these years. And the way we do this is with PERT, right? Our workhorse equation for exponentials. So I'm going to take this guy, e to the RT, and plug that in. Let's see what we get. So starting population is 39.17. This is the California example. And e to the R, I don't know what R is, and T I'm going to put in there as, how many years are we talking about? We're talking about 6 years, okay? 2016 to 2022. Now the final population in 2022 is 38.96. So you can see there's only one variable, R. We're going to figure out what that is. And the way you do that is divide each side to get E by itself. So it's 38.96 divided by 39.17. And I'm going to take the ln of both sides. And what that gives me is 6R over here, right? I got rid of the 39.17 from the right side. I got rid of the E using a natural log. And we just have 6R that's left. So one more step is the easy one, right? We divide each side by 6. So there's my R rate. Okay, that's what R is going to be equal to. And that I should emphasize, this is the California rate right here. So I plug that into my calculator. Let's see what I get. Okay, I get some stuff. I get some decimals here. It's actually a pretty small decimal, but it's negative because population is dropping. And this is, let's see, blah, 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 blah. It's going to be 0.00, some zeros and a 9. So as a percent, remember you have to multiply that by 100. This is going to be negative 0.09%. You should use more digits than this. I'm just rounding to be brief. Now we go through the same procedure for Texas. Okay. And I'm just going to plug this into my calculator. Instead of writing it all down again, it's the exact same idea. You just use Texas numbers, same time period. And what we get here is, let's see, we get a positive rate. Okay, so this is positive 1 point. I'll include more digits here. That's probably the way I should have answered the red one earlier. Now, you have these two rates. How do we actually figure out in what year, this is where it gets interesting, in what year does the population of Texas overtake the population of California? And we're assuming, this is a big assumption, we're assuming California stays slightly negative and Texas stays healthy positive growth rate. That may not be true, but for the sake of this problem, let's see what happens if that plays out. The way you handle this is you set this up the following way. Population of California in some unknown year equals the population of Texas in that same year. And now we plug in the equation, the PERT equation for each of these. So population of California, well, what is that? That is the initial population of California. I'm having trouble annotating here. I'll say initial population of California in some year, which is P initial times E to the RT. And that's equal to the initial population of Texas times E to the RT. Well, I have most of these numbers. My initial population of California, let's just use 2022, okay? Doesn't matter as long as we pick a consistent year and stick with that. So in 2022, the population of California was 38.96 million, and that's E to the r, remember what r is? Negative 0.0009 t. Okay, that's my California side of the equation. And the Texas side of the equation is this, 29.91 million e to the, now we have to use Texas's rate. It's going to be a little different here. This is 0.01153 t. Okay, there's my equation. Think about what this says for a moment. This says the population of California in some year t equals the population of Texas in some year t. We're just going to figure out what t is. So it might look a little complicated at first, but it's really not once you start simplifying some things. Look at what I'm going to do. I'm going to divide each side by 29.91. Okay? That gives us this, 38.96 divided by 29.91. E to the negative 0.0009 t equals, all that's left on the right is e to the 0.01153 t. And now I'm going to divide each side, hold on, by this thing, e to the negative 0.0009 t. Okay, we're going to get all my e's over on one side. You might remember this from how we set up the theory of exponential equations a while ago. So what happens? I mean, obviously, the left side cancels out kind of nicely, and I just get 38.96 divided by 29.91. On the right side of the equation, it's the same exponential, e. And now, what do I get? I get e to the 0.01153 t minus, because of that division, negative 0.0009 t. This uses one of the basic rules of exponents, which is that when you divide two exponents, when you divide two exponential functions, you subtract the exponents themselves. Do we have an example of this? Here we go. Quotient rule, right here. That's what I'm using. Freeze the screen there if you like. Take a look at what we're doing, but I am subtracting two exponents. And what that equals is e to, well, you know, I think at this point we can, calculator. I have no idea what that number is. 0.01153 minus negative 0.0009. Okay, great. So I get e to the 0.01243 t. Okay, and now we do the natural log of each side. So that's going to give me natural log, this problem takes a little while, 38.96 over 29.91. I think we've made the key breakthrough here, which is setting up equivalent equations. And now at this point, you're just going to divide each side by that decimal. And let's see what we get. Let's put that in here. Okay. So I get t equals 23 point some stuff. Okay, which means 23 years after the year 2020. That was, remember, that was what I set as my initial population. So in this case, that would be 2043. But that's going to vary a lot depending on which years you use to calculate your growth, right? And this is what makes demographics sometimes complicated. If you've got one state, here's California, right? All we know is that recently it started declining its population. And if you compare that to Texas, okay, there's Texas. Now, if those continue and you used these 2 points, then sure, California's got a negative growth rate. But if you said, hey, I don't really think California's growth rate is going to stay negative, let's go back further like this. Well, now California's rate looks a little positive. Not as positive as Texas, granted, but still positive. So that would take longer until those two curves met. So modeling is complicated. It really comes down to what you assume at the beginning, but we try our best.